Okay, hello everybody. Mr. Tao here again. Okay, so today I'll be covering this binomial distribution. Okay, under statistics. All right. So the objectives today, okay, will be to learn the key features of binomial distribution model. Okay, we're going to give a quick derivation of it. Next, we'll need to identify scenarios in which binomial distribution can be applied. And lastly, we'll apply the model to solve questions. All right. Can so remember, the last time when we talk about this discrete random variable, we talk about this thing called the statistics. Okay, statistics here actually consists of 4 parts. Okay, the first part is actually data collection. All right, that's step number 1. Step number 2 is data analysis. Okay, third part here is model identification. All right, and then the last part is to use model application, okay, or prediction. All right. So what we are going to do here for our syllabus, we are not going to focus on step 1. We are not going to focus on step 2, but instead we'll jump straight to 3 and 4. All right. So today we are going to talk about this first model. All right. We call this binomial distribution model. Okay. So we are going to discuss what this model is about, how is it being derived, and what kind of situation or what kind of data can it be applied to. All right. Okay. So without further ado, let's move on. Okay. Okay, so what are the key features of binomial model? Okay, so what we're going to do here is we're going to derive the binomial model through a simple example. Okay, so this example here will be a coin toss experiment. Okay, so this coin toss is being tossed 15 times. Okay, and we are asked to find the probability of obtaining 3 hits. Okay, so we are going to use this probability approach. Okay, when we say probability approach means we are using the theoretical probability approach. All right. So over here, we are going to let x be the number of hit obtained. Okay. So what we need here is the probability of x is equals to 3. So using a theoretical approach, all right, since the coin is tossed 15 times, all right, so we'll use 15 choose 3. Okay. And theoretically, the probability of getting a hit is 0.5. So it's 0.5 to the power of 3 because 3 hits, all right? 0.5 times 0.5 times 0.5, all right? Followed by another 12 tails. So the 12 tails will be also 0.5 raised to the power of 12. Okay, so theoretically, we can calculate the probability of getting 3 hits. Okay, 15 choose 3 times 0.5 to the power of 3 times 0.5 to the power of 12. All right, so if you were to extend this calculation, all right, to other outcomes. So for example, if I want to find the probability of getting 6 hits, okay, this will be Px is equals to 6. And we can see that in this case, we just have to modify what we have done a bit, which is 15 choose 6, multiplied by 0.5 to the power of 6, and 0.5 to the power of 15 minus 6. All right, so we can see that whatever number that we put here, all right, we just need to put the same number here, all right, because I want 6 hits. So out of 15 throws, I can choose 6 of it to be hit. All right, and the probability of 6 hit, okay, means it must be raised to the power of 6. And since the rest are tail, meaning to say that we use the total number of tosses minus away the required, which is 15 minus 6. All right, and so this will be how we calculate the probability. So we can extend this even if it is Px equals to 15, so the formula can be written this way. Okay, so from here we can deduce what is the general formula for the outcomes of such scenarios. Okay, so it will be Px equals to R, N choose R, PR, and Q to the power of N minus R. All right, so what we have here, all right, is what do we have here? Okay, whereby this, sorry, let me just adjust it back. okay, what we have here is n. Okay, n in this case represents the number of trials. Okay, n represents the number of trials, meaning the number of times we do the experiment. Okay, so in this case, we are going to do the experiment 15 times, so n is equal to 15. R is the desired outcome, okay, meaning the number of hits for this case. If I want 3 hits, R will be 3. If I want 6 hits, R will be 6. If I want 15 hits, R will be 15. And in this case, P, okay, the P value that we use here is the probability of success. So today, if it is a coin toss, the probability of success is simply half. All right, and Q is the probability of failure. Okay, so since this is there's only one event space, this event space consists of either head or tail, meaning to say that Q must be equal to 1 minus P. All right, so for the coin toss experiment, Q will be half also. Okay, Ken? So ladies and gentlemen, what we have here is actually our binomial model. Okay, this is our binomial model. All right, so okay, so we have actually completed the derivation of binomial model. Okay, which one is our binomial model? The binomial model is actually represented by this equation over here. Okay, and the parameters have this meaning. Okay, so from this experiment or from this example, we can infer that what are the key features of this model. So to be able to use this model, all right, firstly, the experiment must have n discrete number of trials. That means I must be able to do the experiment n times discretely. 1 time, 2 times, 3 times, 4 times, 10 times, 15 times. Okay, and since that's the case, what we are considering here is a discrete random variable. Okay, because the x value or your random variable can only be taken as discrete values. Okay, and for each experiment or each trial, okay, we should have 2 outcomes only. So just like the coin toss, for each experiment, either I get head or tail. Okay, so so long as you have any scenario, okay, that fulfills the above 2 features, okay, we can fit it with a binomial model and use it to compute the probabilities. Okay, including things like the number of times a student is late for school and the number of times it rains a week. All right, so this here is actually a statistical model, okay, which is derived from theory. Okay, then you might be wondering, where is the statistics part? Okay, the statistics part is actually, it will come from the value of P and your value of Q. Okay, this has to be determined statistically. All right, so we are going to use this model to calculate any scenarios that have n discrete number of trials, and each trial must have 2 outcomes. All right, okay, let's move on. So for this model, okay, it must also have certain assumptions. Okay, so what are the assumptions that we can have? Okay, the probability of each outcome must be fixed. That means every single time I throw a coin, the probability of getting hit must be half, 0.5. It can never change. Okay, if it changes, then this model will not work. All right, the outcome of each trial must be independent of one another, meaning the first time I throw the coin must be independent on the second time I throw the coin. Okay, every throw must be unbiased. Okay, Ken? So long as these 2 assumptions are valid, okay, please feel free to use the model. All right, so just to summarize, when can we use the model? We can use the model for situations whereby there are n number of times I conduct something. And each time I conduct that thing, it must only have 2 outcomes. Okay, so if this is the scenario that we have, then we can apply the binomial model. And on top of that, when we apply this model, we are making 2 assumptions. The first assumption is that the probability of each outcome must be fixed. It can never change, meaning the P value and the Q value must be fixed. Okay, and the other assumption is that the outcome of each trial must be independent of one another. Okay, and since we are looking at statistics, it's important to be able to compute some statistical parameters. Okay, the first one is your expectation. Okay, this is your expectation, or we call it the mean. Okay, so the mean of a binomial model is given by NP. Okay, whereby N is the number of times I do it, P is the probability of hits. Okay, this is actually a very common sense formula, NP. For example, using just now the example that we used, okay, the number of times you throw the coin is 15. The probability of getting a hit is half. So meaning to say that we'll be expecting ourselves to get 7.5 times hit in the experiment. All right, which is very logical. Okay, so the next parameter that we'll compute is actually our variance. So variance is given by MPQ. Okay, so remember your Q value is 1 minus P. Okay, and then the last thing we have here is actually our mode. So what is the mode? The mode is the highest probability that we have. Okay, the occurrence with the highest probability. Okay, and we will further discuss this concept later on in one of the example. Okay, so for this case, for now, we can take these two formula first. Okay, so the mode can be computed by MP plus P. Okay, so this first case is actually for a single mode case. So this is a single mode. That means there's only one highest occurring value, single mode case. All right, and if it is a decimal, please round down. Okay, the second formula, okay, for mode is for a bimodal case, meaning to say that there can be two modes. All right, so the two modes will be simply given as MP plus P or MP plus P minus 1. Okay, so this will be considered bimodal if MP plus P itself is already an integer. Okay, so a simple way to visualize is single mode. Okay, usually the value we'll get will be things like 3.6. Okay, so if it is a 3.6 value, all right, we'll need to round down to give you 3. So the mode in this case is 3. All right, and then if it is a bimodal case, then this mode itself, MP plus P, okay, probably will be giving you a value like 2. Okay, so if the first value is 2, then the next value must be MP plus P minus 1, so which is 1. So for the bimodal case, I will have 2 modes, and for the single mode case, I will only have 1 mode. Okay, guys, give me 1 second. Okay, sorry, I'm back. Okay, so we'll discuss about this mode subsequently in the question later on. Okay, so just bear in mind we have 3 statistical parameters we're interested in: the expectation, which is also the mean, the variance, okay, and also the mode. All right, so let's move on. Okay, so we are ready to actually do some problem solving. Okay, basically what we need to do here is to apply this binomial distribution model. All right, and for our syllabus, more or less, this is actually under calculator work. Okay, so for the calculator, I'm not able to show the graphic calculator here. Okay, on my computer, right? Because recently they have restricted the free use of this graphic calculator UI on the computer by the Texas Instrument. Okay, but nevertheless, okay, you can press it by yourself. I believe for those who have learned it, you should be able to press it. Okay, so you must go under your stats. Okay, so the 2 things that we are going to use is actually your binomial PDF and also your binomial CDF. All right, so we are going to discuss the 2 differences. So first part, some calculator work first. Okay, so how are we going to do the calculator work? All right, so say for example, if we have x follow a binomial of 15, 0.3. Okay, so what does this mean? Okay, it means, so this binomial model is actually declared this way. So if something were to follow binomial, I have to declare it to follow binomial given NP. Okay, whereby n, as we discussed, is actually the number of trials. Okay, and p is actually the probability of success. All right, Ken. So there's no context for this part. We just want to do some calculator work and take note of some mathematics that involve pressing of the calculator. Okay, so for example, if I have x given to be np, meaning to say n is 15, okay, number of trials is 15, probability of success is 0.3. All right, Ken. So we are asked to find the following values. Okay, just clear it. Okay, so for the first part, okay, part one, okay, for part one, okay, px is equals to 2. Okay, so for this part, you can simply press your calculator under binomial PDF. Okay, binomial probability distribution function. Okay, this gives you the exact value of x equals to 2. All right, so if you press a calculator, this will give you 0.0916. So I take note, for this instance, we will use the PDF. Okay, because it's calculating exact value, x equals to 2. Okay, so next, moving on to part 2. So what if I want to calculate px less than or equals to 3? Okay, what does this mean? This is actually equivalent. If I were to break it down, this will be px is equals to 0 plus px is equals to 1 plus px equals to 2 plus px is equals to 3. So this here, less than or equals to 3, is indicative of a cumulative. All right, so if you want to press this on a calculator, all right, you got to use the CDF function, the binomial CDF function. All right, Ken. So if you were to press it in your calculator, it should give you 0.2969. Okay, take note, because this is a discrete random variable, DRV. Okay, so whatever that you press in your calculator, it will assume that there's an equal sign here. Okay, Ken. That means when you go to this CDF, binomial CDF, when you key in n is equals to 15, p is equals to 0.3, and x is equals to 3, is assuming this format. It's assuming that the thing that you want to calculate has an equal sign. Okay, so essentially speaking, okay, whatever that you want to calculate from your calculator, okay, if it is a DRV, okay, your CDF, it must have the equal sign. Okay, so I shall refer this as a DRV format. Okay, so later on in this lecture, whenever I talk about this DRV format, okay, it's automatically assumed that you need the equal sign. All right, okay, so this is a DRV format. So what is the importance of this DRV format? So let's look at part 3. Okay, so part 3, we're asked to calculate px less than 4. So this is not a DRV format because there's no equal sign, correct? There's no equal sign. All right, so mathematically, we need to convert it first before we press the calculator. So px less than 4. All right, so this is equivalent to px less than or equals to 3. All right, so we have to convert this into the DRV format. Okay, so once we have done that, we can press the calculator. So when expected, this value will be the same as 2969. Okay, Ken. So then what about other scenarios? So let's say if I have part 4, what if I have px more than 5? So clearly this is not in DRV format. Okay, another restriction that the calculator can have is that it cannot calculate anything that is not in the DRV format. So this is not in the DRV format. So we have to change it into a DRV format. Okay, so we can make use of the complementary case. Okay, so the complementary case is written as 1 minus p x less than or equals to 5. Okay, so once I convert it into this case, this part here, I can press the calculator. Okay, so this part can be calculated from the calculator, and then the value we'll get is 0.2783. All right, can. So remember the DRV format, okay, should be strictly adhered to. Okay, it must be less than or equals to before the calculator can press for you. Anything that is not, you must change it. So if I have the case of less than 4, I must change it to less than or equals to 3. If I have the case of more than 5, I can change it to the complementary case, which is 1 minus px less than or equals to 5. All right, can. Okay, next, moving on. Part 5, okay, we have the other scenario. What if I want to find a sandwich value, P6, between x and 8? Okay, so how are we going to calculate this value here? Okay, again, the calculator doesn't enable you to find out this sandwich value, so we need to break it down. Okay, so how do we actually break it down? Okay, we can actually analyze this inequality. Okay, a simple way to put it is I can rewrite it into px less than or equals to 7. All right, minus away p, in this case, x less than or equals to 7. Okay, actually this question here doesn't make sense. This is not a very good question. All right, maybe let me just because if you look at this, sorry, if you look at this, okay, px between 6 and 8. All right, if you draw a number line, okay, the x value, okay, 5, 6, 7, 8. So if x is between 6 and 8, there's only one value, okay, which is 7. So this here is actually equals to px equals to 7. Okay, then from there you can press your PDF calculator. All right, maybe I just modify the question a bit to show you how do we transform if needed. So p, if let's say I have 3 x less than 8. Okay, can. So to convert this, okay, I must change it to px less than or equals to 7 minus away px, all right, less than or equals to 3. All right, can. So how did I get this conversion? All right, you can actually draw the number line. Okay, can. So today, all right, let has the value 3, 4, 5, 6, 7, 8. Okay, so between 3 and 8. All right, so let's look at the first part first, the 8 one. So this is must be less than 8. Less than 8 means it cannot include 8. So it cannot include 8, it means it must start from 7. So x less than or equals to 7. So this is the first part. All right, I say again, when we consider x less than 8, because it doesn't include 8, so actually we start from 7. So x less than or equals to 7. Okay, then the next part, x must be more than 3. Okay, x must be more than 3. Again, it cannot include 3. Okay, it cannot include 3. All right, can. So if it cannot include 3, if I were to subtract something, all right, I have to subtract from 3 onwards. Correct. So if I use the blue line minus away the green line, all right, it will give me these values here, 4, 5, and 6. All right, can. So at the end of the day, we can change it to px less than or equals to 7 minus px less than or equals to 3. Okay, hopefully everybody can see this. If you cannot see this, please try to draw your number line. Okay, so today if I want x to be between 3 and 8, non-inclusive, okay, the subtraction that we can find or we can use is px less than or equals to 7. This one, the first one should quite clear cut because x less than 8, meaning to say that x cannot be 8. So I must start with x less than or equals to 7. Minus away, okay, the back part is because I cannot include 3. So the subtraction must start from 3 itself. All right, so if I do this subtraction, I will get 4, 5, 6 in this case. All right, can. So this is the second scenario that we can see. okay, that we need to know how to press the calculator. Okay, so then next, moving on to part 6. Okay, so there can be a question where I ask you about the least value of r such that px more than or equals to r must be less than 0.1. All right, so what they are looking for here is actually your r value. Okay, Ken, so how do we do this? Okay, that means, you see, we are going to start off with x more than or equals to r less than or equals 0.1. Okay, so firstly, to solve this, all right, we need to change this into your DRV format. Is this a DRV format? No, this is not DRV format. Okay, so how are we going to change it to DRV format? This will be 1 minus px less than r less than 0.1. So first, I take the complementary. Okay, I take the complementary case. Okay, Ken. Next, I will shift my 1 to the other side. Okay, so this is 0.9. Okay, this is still not in DRV format. Okay, because it's going to be x less than r, so it cannot include r, meaning to say that this must be x less than or equals to r minus 1. So you need to do this manipulation first, okay, before you press the calculator. Okay, so to press the calculator, very simple. Okay, you need to use the table function, meaning to say that you need to key in your equation under the graphing y equals to. So go under y equals to, okay, and key in your binomial distribution. So y equals to, then go to stats, okay, then choose your binomial CDF. Okay, then you insert. Okay, once this is done, you will go to the table. Okay, so the table will give you the set of values. Okay, Ken. So the table will give you the set of values that you need. So in this case, all right, from the table, okay, we can actually observe that r minus 1, okay, is going to be equals to 7. All right, so r in this case will be 8. Okay, so this has to be calculated from this thing called the table function. Okay, I will show this later on in detail when we go into the question. Okay, now just briefly going through how to calculate these values, okay, using your GC. Okay, Ken? Okay, next, how about the next case? The last case that we can have is we are asked to calculate this n. So today, the unknown can lie in this n value. So for example, I've given you everything except for the n, okay, such that px less than or equals to 3 less than or equals to 0.5. So how do we calculate the n value? So same thing, first thing, check that this is in DRV format. Yes, this is in DRV format, no problem. Okay, Ken, so we are still going to use back the same step. We are going to use table. Okay, so part 6 and 7 is the same step. We must use table. So y equals to, go to stats, go to binomial, CDF, okay, then you insert, okay, then you press enter, then you go to your table. Okay, so from the table, you will search for the probability that is less than 0.5, and this will give you n is equals to 12. Okay, again, I will further detail this later part when we come into the question. Okay, so that's it for question 1. So the importance of question 1 is that you must be able to perform the calculator work for all of this 1 to 7. Okay, these are all the possibilities that we can encounter. Okay, let's move on. Okay, so moving on. Oops. Let me get my... Okay, moving on. Okay, let's move on to the first actual example with a context. Okay, so we have an archer which has a 0.2 chance of hitting the bullseye. He shoot 10 arrows. Okay, let the random variable x be the number of times he hit the bullseye. Okay, so in this case, this will be an example of a binomial distribution. Why? Because he What he is doing here is 10 discrete trials or 10 discrete experiments, shooting of 10 arrows. And for every time you shoot the arrow, there's two outcomes. Either you get a 0.2 chance of hitting or you get a 0.8 chance of not hitting. Okay, so clearly this is a binomial distribution. So once this is confirmed, we can write it down, NP, so N is 10 and P is 0.2. That's it. Okay, part 2, what is the probability of him hitting the bullseye 4 times? Okay, can. So this will be Px is equals to 4. So you press the calculator, it must be PDF. All right, it should be 0.0881. Okay, part 3. What's the probability hit the bullseye at least 4 times? Okay, at least 4 times. So this translates to a inequality of more than or equals to 4. Okay, is this the DRV format? No, this is not the DRV format, so we have to change it. So first we use the complementary case, 1 minus Px less than 4. And then we further reduce it to 1 minus Px less than or equals to 3. So this part here is your DRV format, which you can press a calculator. All right, so if you press it, it'll be 0.1209. Okay. Can? So actually, although this is a very simple question, but this question highlights one important point. The format of answering a statistical question, no matter whether it's binomial or later part, we are going to learn normal. It's always as simple as this. We always declare the variable first. We write down the model, then we formulate. It's actually a 3-step process. It shouldn't get any more complicated than this. Okay, so if you find yourself writing more steps than this, means something is wrong. It shouldn't be complicated. All right, it should always be this 3-step. First, declare a variable. Second, write down your model. Third, formulate the problem. That's it. Then the rest is calculator work. All right, that's why all along, statistics, okay, has been a very happy section or happy chunk of H2 maths for most students because it's easy. So don't make it complicated for yourself. All right. Okay, let's move on. Okay, question 3. A multiple choice consists of 8 questions. Each question has 5 options and only 1 correct answer. To pass the test, one has to answer 5 questions correctly. John took the test. Okay, can find a probability that he answers all questions correctly. Okay, so as I say, 3 steps. Okay, so what is your step 1? Declare your random variable. Okay, can. So the random variable today will be let x be the number of correct question. Remember, the declaration is always a very overlooked portion of statistics. But in fact, the declaration of the random variable is the most important because it determines how you look at the question. If you cannot define it properly, it means you don't understand the question at all. All right, so today x should be the number of correct question. So x will follow a binomial distribution of total 8 questions. Okay, and the probability of getting each question correct is 1 out of 5. Okay, so this is step number 2. And to find the probability, answer all the questions correctly. This will be Px is equals to 8. All right, okay, because there's total of 8 questions. Okay, so this is going to give us a very small value, 0.0000256. Okay, can. Okay, next part 2. What is the probability of him answering between 3 to 6 questions correctly? So what they want here is Px between 3 and 6. Okay, so we have to convert this. Okay, we got to break it down. Okay, so since the first part here, less than or equals to 6. So we'll start off with Px less than or equals to 6 because it must include 6. Okay, minus away Okay, the second part, more than or equals to 3. So it must include 3. So when I subtract, it must be px less than or equals to 2. All right, because I want from 3 to 6. So if I break this down, it should be from x less than or equals to 6 minus away x less than or equals to 2 because I want to include 3. All right, so this value here will give us 0.2031. All right, Ken. So that's it for part 1 and part 2. Let me erase. Okay, so we'll keep the model because the whole question will follow the same model. Okay, so next, moving on to part 3. What is the probability that he will pass the test? So sometimes the question can be asked indirectly. So the probability to pass is what? The probability of him answering at least 5 questions correct, right? So doesn't have to be exactly 5, but just at least 5. So x must be more than or equals to 5. Right? Is this in DRV format? No. Okay, so we have to change it. So take on the complementary case, x less than or equals to 5, and then further reduce it to x less than or equals to 4. All right, so you press the calculator, this will give you 0.0104. Okay, so that's it for part 3. Okay, the last part, part 5, find the expectation and variance of the test. Expectation, okay, we follow the formula, NP. So this will be 8 times 1 over 5. Okay, so this will be 8 over 5. Variance will be NPQ. Okay, Ken, so for the NPQ value, okay, take note, what is your Q? Okay, Q is 1 minus P. So this is 8 times 1 over 5 times 1 minus 1 over 5. Okay, so this value here will be 32 over 25. And this will be 1.28. Okay, so again, another simple question to build the basics. Okay, let's move on. Okay, let's move on to question 4. Okay, whereby we see another category of question. So we have a certain large city. 1 in every 10 person is a left-hander. Find the probability that the randomly chosen sample of 10 people, more than 1, but less than half of the sample will be left-handed. All right, Ken. So for part 1, we'll define, okay, we let x be the number of left-hander in 10 people. Okay, so we'll define this as binomial distribution, okay, 10 people, and the probability of being a left-hander is 1 in 10, so it's 0.1. Okay, we formulate the problem, probability of more than 1, but less than half of the sample. Okay, half of the sample means 5. So more than 1, but less than 5. Okay, Ken? So in this case, we need to break it down. Okay, so for the first part again, all right, x less than or equals to 5. So it doesn't need to include 5. So we will start off with px less than or equals to 4. Minus away the second part, x more than 1. More than 1 means I do not need to include 1, so I can subtract it away. So x less than or equals to 1. Okay, Ken? So you calculate this, it will give us the probability of 0.2623. Okay, Ken? Next, move on to part 2. Find the mean and variance of the random sample of 25. Okay, so this question here, I just want to show you that sometimes the sample size will change. So in part 1, the sample size was 10, but part 2, the sample size was 25. Okay, so if the sample size should change, by right, we have to change the random variable also. Okay, so maybe we let k be the number of left-hander in 25. Okay, so to be strict, if you change the sample size, we must change the random variable. So K will be binomial 25, 0.1. Okay, so to get the expectation, EX will be equals to NP, which is 25 times 0.1. So it's around 2.5. Okay, can? And then next, if you need the variance, okay, can? So this will be var X will be NPQ. Okay, can? So this will be 25 times 0.1 times 0.9. All right, and this value here will be around 2.25. Okay, can? So part 2 is just to show that if you change the sample size, by right, you have to change the random variable. Okay, next, let's move on to part 3. Okay, part 3, they ask us to find the most probable number of left-hander. So what they want here is actually the mode. Okay, can same thing, sample size has changed, so maybe let us redefine it. Let maybe A be the number of left-hander in 25 people. Okay, so A follows a binomial of 45 and 0.1. So how do we get the mode? Okay, so actually we can use the formula that was provided just now. The mode can be calculated by using MP plus P. All right, so in this case, MP plus P will give us the value of 4.6. Therefore, the mode will be a round down, which is equal to 4. Okay, alternatively, all right, what you can do, okay, which most schools will ask you to do is to use the table. So same thing, okay, what you need to do, all right, is to key in your y equals to, okay, can. Then you have to key in your binomial, okay, distribution. Okay, in this case, the binomial distribution is binomial PDF. All right, the unknown here will be x equals to x. Okay, then your calculator, you need to go to your table. Okay, the table function. So under the table function, it will show you this table over here. Okay, I'm still going to write some values here. So maybe 2, 3, and 4. All right, can maybe I change a bit, erase the 1, 2, 3, 4. Maybe I use 3, 4, and 5. Okay, so either way is displayed in your calculator. Okay, so the value of 3 is 0.1699. Value of 4 is 0.1982. Value of 5 is 0.1806. Okay, so from the table, okay, this value is your x. All right, this x here is the x value when you calculate px equals to x. Okay, over here is px equals to x itself, the probability. So as I said just now, the mode is the highest probable value. So from the table, you can actually see that the probability is the highest when x is equal to 4. Okay, so therefore, x equals to 4 is your mode. All right, therefore x equals to 4 is your mode. Okay, so you can choose 2 methods, either this or this. All right, but I believe the table method is what most schools will prefer. All right, Ken? So this is part 3. Okay, let's move on to part 4. How large must the sample be so that the probability so that it contains at least 6 left-handers is at least 0.95? Okay, so where is this unknown? The unknown for part 4 is how large the sample must be. Okay, so the unknown, okay, let us define first. Let y be the number of left-hander in n sample. All right, so y will follow a binomial distribution of n 0.1. So for this question, the unknown is actually in n. Okay, the unknown is actually in n. All right, can. So how do we calculate n then? Okay, we have to, again, still we stick to the formulation. The formulation is it consists of at least 6 left-handers is at least 0.95. So the probability of y at least 6 is at least 0.95. So how do we calculate n? Okay, same thing, we need to change this into DRV format. So this will be 1 minus p, y less than 6, more than or equals 0.95. Okay, can. So then we continue to change it to y less than or equals to 5, less than or equals to 0.05. All right, can. So to get this unknown, the n value, we have to use again the table method. Okay, so from a calculator, same thing, we go to y equals to, we key in our binomial, in this case is CDF. Okay, under binomial CDF, okay, n today is my unknown, p is 0.1, x is equals to 5. Okay, and so this is our binomial CDF. Then we go to the table. Okay, so from the table, what should we be able to see? So same thing, the table will have 2 columns. So the first column is n. Okay, in this case, you got to search a bit because what we want is the probability of y less than or equals to 5 to be less than or equals to 0.05. So if we search, the n value, okay, must go to somewhere close to 90. Okay, so I'll show 2 values, 91, 92, and 93. So 91 will be 0.0540. 92 will be 0.0514. 93 is 0.0489. So what this says, or what this indicates, is that when n is chosen to be 93, your probability of y less than or equals to 5 falls below 0.05. Therefore, the answer, what we need, is n equals to 93. Okay, can? Good. All right, so question up to question 4, these are all the basic questions. Basic question in the sense that these are the ways they can test you. All right, they can either test you directly, or they can ask you to find your n value, or they can ask you to find your x value. Okay, for the n value and x value, you must use the table method. All right, can? Okay, so this is it for the tier 1 question. Okay, so we need to move on to the more difficult kind of question, which is the tier 2 problems. So what is the tier 2 problems? We will use this example to show. Okay, so in a phone manufacturing plant, it is found that 5% of the phone are defective. Okay, during a small scale quantity inspection, a sample of 10 phones are examined. Find the probability that not more than 2 phones are being defective. Part 1 is simple. We let X be the number of phone defective. Okay, can in 10. All right, so X will follow a binomial of 10 phones. All right, and the probability of being defective is 0.05. Okay, so we formulate probability of not more than 2. So X must be less than or equals to 2. All right, Ken. So press your calculator. Is this in DRV format? Yes. So this will give us the answer straight away. Okay, so the tier 2 problem will come in part 2. In a larger scale like inspection, 10 batches of such samples were examined. Find the probability that at most 2 batches will contain not more than 2 phones being defective. So why is this a tier 2 problem, or what is this question asking about? Okay, some of you might be confused when you see this question. Okay, what it is saying is that 10 batches of such samples. Each sample is consisting of 10 phones. So we have 10 batches, batch 1, batch 2, batch 3. So each batch consists of 10 phones, 10 phones, 10 phones, all the way up to the 10th batch. So they want to find the probability that at most 2 of these batches will consist no more than 2 phones that are defective. Okay, within each batch, 10 phones, the probability of having no more than 2 phones defective is 0.09985. Okay, so this probability here is within each batch. Within each batch, not more than 2 phones being defective is 0.9885. So today, I want at most only 2 of such batches. 2 of such batches to have no more than 2 defects. So I need to redefine my variable. So this is where the definition of the variable is important. Let y be the number of batches out of 10 to consist no more than 2 phone defective. So y is the number of batches. So it follows the binomial 10 batches. And the probability of each batch having not more than 2 phones being defective is actually 0.985. So what we have done here is we have taken this probability and put it here. This is my tier 1. This is my tier 2. Okay, can you see? That means I'm grouping it into a larger perspective. 10 batches with no more than 2 batches that consist no more than 2 phones being defective. Okay, can? So what they want here is the probability of x less than or equals, probability of, what they want here is probability of y not more than or equals to 2. Okay, can? The probability here is going to be very small. It's going to 1.34 times 10 to the power minus 14. Okay, but doesn't matter. Most importantly is you must understand the way this question is being written. This is a very difficult question for some of the students. Okay, if you have difficulty in understanding this question, please just memorize it. Memorize how this question is being done. Basically, if I regroup it into larger batches, I will take the first probability and put it into the second distribution. That's it. The whole thing will only make sense to you if you define your random variable properly. All right. Okay, don't worry. Let's move on and look at more examples of this. Okay, question 6. Question 6 is not so guided. Okay, like the first, just now question 5 was guided because it asks you to calculate the tier 1 probability first. So in this case, we need to find out what is the tier 1 probability. So we have a DBX bank, 10 branches in Singapore. Each branch is manned by 8 staff. Each staff will receive a complaint in a single day is 0.5. Find the probability that there's no more than 6 branch with at least 2 staff receiving the complaint. So what grouping do we have here? We have 10 branches. Branch 1, branch 2, branch 3, and branch 10. Each branch has 8 staff. So we want to find no more than 6 branches with at least 2 staff receiving the complaint. So the tier 1 probability actually lies here. The probability of 2 staff receiving complaint. So we need to define this first. So let X be the number of staff receiving complaint in one branch. So X, one branch, there is 8 people and the probability of receiving complaint is 0.5. All right, so P X at least 2 staff, more than or equals to 2. Okay, this is what they want. Okay, so please convert 1 minus px less than or equals to 2, which is 1 minus px less than or equals to 1, and this will give you 0.9648. Okay, so this is the number of staff receiving a complaint within one branch. So next, we'll define our tier 2. Let y be the number of branch in 10 branches which have at least 2 staff receiving complaint. Okay, so y will follow a binomial distribution. In this case, I have 10 branches, and the probability, okay, is 0.9648. The probability of within one branch is either you receive more than 2 complaints, at least 2 staff receive more than 2 complaints. Okay, so the probability here is I'll put it from the first part. Okay, so what do they want us to calculate? P no more than 6 branch. Okay, x less than or equals to, sorry, how am I writing this wrong again? P y less than or equals to 6. Calculate it properly. All right, you should get 0.0003. Okay, so this is another example of a tier 2 problem. Okay, I'm going to show one more, okay, before we end our lesson here. Okay, so most importantly, you must understand the types of question that will be asked. Know how to press the calculator. All right, and the highest level, okay, is to be able to understand and solve these tier 2 problems. Okay, so we have a chain with 50 links. When a chain is used to handle a certain load, all right, the probability that a link will break is 0.08. Find the probability that the chain will not break. Okay, so for part 1, we define let x be the number of links. All right, in this case, let me see that break. Okay, so x will follow a binomial of 50 links and 0.08. So if I want indirectly chain unbroken is equivalent to saying as px is equals to 0. So this will give us 0.0155. Okay, so again, this is an indirect asking of the question. Part 2, the number of such claims are used to hang the same load. Find the least number of chain that is required that the probability of one chain breaking will not exceed 0.9. So this is a tier 2 problem. Okay, so we are going to use a couple of these chains, okay, to hang a certain load such that the probability of one chain breaking will not exceed 0.9. And where is the unknown? Okay, so let me define first. Okay, so this is going to be a tough question. So let y be the number of chain breaking in n chain. So where's the unknown? Unknown is here, n, in the number of trials. So y will follow a binomial of n. Okay, so breaking, what's the probability of breaking? The probability of not breaking is 0.0155. So the probability of breaking is 1 minus 0.0155. So again, this is a tier 2 problem if you define it properly, and the unknown is in n. Okay, so we formulate the problem. Okay, probability of one chain breaking does not exceed 0.9. So P y is equals to 1 will not exceed 0.9. So since I want to find n, so I must use my table. Okay, so using back the same method, I'm going to press the table. Okay, so the unknown here is my n. The probability that we are going to look at is py equals to 1. So at very small values, n equals to 1 and 2, this probability is 0.9845 and this is 0.0305. So clearly, when n is 2, the probability of y equals to 1 drops drastically. So therefore, n must be 2. So the person must be using at least 2 chain to hang this load. All right, Ken. Okay, Ken. So hopefully you learn a bit from my this very short lecture. All right, Ken. Of course, there's a few more questions that is out there, but I believe I've covered the core of it. Okay, the rest of the question probably is just a reshuffle or remanipulation of what I covered today. So most importantly, you must know how to do the calculator work. Most importantly, you must understand that there are two types of problem. One is the tier 1, one is the tier 2. Okay, so for tier 1, okay, let me just give a quick recap. For tier 1, all right, because binomial is usually defined this way, okay, and then given by a formulation, okay. So there's a few places whereby unknown can be, the unknown can be here, the unknown can be here, the unknown can be here, or the unknown can be here. Okay, if the unknown is here, this is the most direct. This one is the direct one. You can just press the calculator. Okay, the unknown is anywhere this tree, you must use your table. Okay, so this is generally for tier 1. Okay, of course, it can ask you about the mean, the variance, and the mode. All right, and of course, you must be familiar with your tier 2 questions. Okay, so with that, I end my session for today. Thank you so much for joining me. I will see you again. Bye-bye.